Welcome back, everyone. If you're gearing up for the rigorous CSS General Science Ability exam, or, honestly, if you're just fascinated by disaster management, you have landed in the exact right place. I'm your senior examiner, and today we're breaking down the Earth's most catastrophic hazards in this explainer. We're going to start from the incredibly volatile Pacific Ring of Fire, that massive horseshoe of seismic chaos where tectonic plates continuously collide. Our goal today is to rigorously dissect the exact scientific mechanisms, the cascading impacts, and the strategic mitigation frameworks that you absolutely need to master. Okay, let's dive into this. We've got a tight 5-part syllabus today: dynamics of Earth hazards, volcanoes, tsunamis, avalanches, and disaster risk reduction.
Starting with Part 1, Dynamics of Earth Hazards, the underlying forces.
Moving right into Part 2, Volcanoes, Mechanisms and Impacts. So what actually is a volcano when we get down to the exam-level definition? Based on frameworks from the U.S. Geological Survey and the Smithsonian's Global Volcanism Program, it's essentially a geological formation where molten rock, ash, and gases escape from deep below the Earth's surface. Now, this whole system is primarily driven by either tectonic movement, think subduction zones, or by massive mantle plumes we call hotspots, which actually operate completely independent of plate boundaries. Think of the eruptive process as a perfectly logical kinetic chain. Step 1 is magma formation, happening deep down in the mantle. Step 2, we get pressure building up within the crust as gases rapidly expand. It's kind of like shaking a soda bottle. Step 3 is the actual eruption at the central vent or crater. And finally, Step 4, the massive release of ash and lava flows. It's a remarkably simple yet terrifyingly elegant sequence of thermodynamics and pressure release. And the physical shape of a volcano brilliantly illustrates how it's going to erupt. Morphology dictates the eruption style. Take shield volcanoes, like Mauna Loa. They are broad, they have gentle slopes, and they produce non-explosive, effusive lava. Now compare that to composite or stratovolcanoes. These are your steep, highly explosive hazards driven by thick, high-viscosity magma, perfectly exemplified by the catastrophic 1980 eruption of Mount St. Helens or the 1991 eruption of Mount Pinatubo. Then, of course, we have smaller, steep cinder cones and fissure volcanoes, which literally just erupt through linear cracks in the Earth. When you're analyzing impacts, you've really got to separate the primary effects from the secondary ones. Primary hazards happen instantly. We're talking lava flows, massive ashfall, and crucially, pyroclastic flows. Make a note of that one, because pyroclastic flows are responsible for the vast majority of volcanic fatalities. Secondary hazards include debris lahars, which are essentially boiling mud flows. And beyond the immediate localized destruction, we see massive economic impacts like entirely halted aviation and profound global climate effects. For instance, that Mount Pinatubo eruption actually caused short-term global cooling because it injected huge volumes of sulfur dioxide right into the stratosphere.
Shifting gears to Part 3, Tsunamis, Ocean Waves Unleashed.
Let's get one thing straight right off the bat, especially as classified by NOAA. A tsunami is emphatically not a regular tidal wave. It has nothing to do with wind or lunar gravity. Scientifically speaking, it's a powerful, exceptionally long wavelength sea wave caused by a significant vertical displacement of water. That vertical displacement is the absolute critical variable here, and it's usually triggered by undersea earthquakes, volcanic collapses, or massive underwater landslides. Here is the exact chain of events. Tsunami formation kicks off with seafloor uplift at a subduction zone, which is exactly what triggered the devastating 2004 Indian Ocean earthquake and the 2011 Tohoku event in Japan. This violent uplift creates massive water displacement. That kinetic energy then propagates through the deep ocean, finally culminating in what we call the shoaling effect, leading to devastating coastal impact. Now, what's really interesting about this comparison is the physics of that shoaling effect. In deep water, a tsunami is a complete stealth threat. It travels at jet aircraft speeds. We're talking up to 800 kilometers per hour with wavelengths stretching over 100 kilometers. Yet its surface amplitude is incredibly low. You literally wouldn't even notice it if you were out on a boat. But as it hits shallow coastal water, friction slows the front of the wave down, the wavelength aggressively compresses, and all that forward kinetic energy forces the water upward, creating a massive, highly destructive run-up. So what actually triggers these monsters? They basically fall into 3 categories. Tectonic triggers at subduction zones are by far the most common, and frankly, this is exactly why Pakistan's Makran coastal trench remains highly vulnerable to future events. Volcanic island collapses are much rarer but incredibly lethal, as the world saw with Krakatoa back in 1883. And then we have landslide triggers,
perfectly exemplified by the crazy mega tsunami in Lituya Bay, Alaska in 1958, where massive amounts of mountain debris falling into the water generated the wave. The aftermath of coastal inundation is just catastrophic across 4 main domains. Environmentally, you get massive erosion, and saltwater intrudes and ruins freshwater aquifers. The human and economic tolls are staggering, particularly in vulnerable, densely populated coastal zones that don't have adequate early warning systems. Infrastructure, like ports and buildings, face near total demolition. And finally, the health impacts. Contaminated water rapidly leads to awful secondary disease outbreaks. All right, taking things to high altitudes for Part 4. Avalanches, mountain slope failures.
At its core, an avalanche is a rapid, gravity-driven flow of snow, ice, and debris. For regions with extreme elevation, like Pakistan's incredibly vulnerable northern areas, understanding these slope failures is critical. And it's not just about protecting civilian infrastructure, it poses a severe vulnerability to military deployments and seasonal tourism. The absolute foundation of avalanche science relies on understanding 2 distinct things: snowpack stability and terrain characteristics.
So how does the slope actually fail? Well, the sequence begins with snow accumulation and loading. But critically, step 2 involves the formation of hidden, weak layers inside the snowpack. These are often fragile frost crystals known as depth hoar, created by rapid temperature shifts. Step 3 is the triggering event. This could be a heavy new snowfall adding critical weight, or maybe a human skiing right over that weak point. And this immediately results in Step 4, a catastrophic slope failure.
We generally classify avalanches by their composition, and the danger level shifts dramatically between the types. Loose snow avalanches start at a single point in unconsolidated fresh snow. Wet avalanches involve heavy, water-saturated snow. They move a bit slower, but behave almost like flowing concrete. But the most dangerous one by far is the slab avalanche. This happens when a massive, cohesive upper layer of snow breaks off entirely from that weak layer beneath it. It travels with just terrifying speed and mass. The actual triggers for these failures usually come down to a deadly combination of terrain, weather, and humans. The physical sweet spot for avalanches is on mountain slopes pitched between 30 and 45 degrees. Add in climate-driven variables like rapid temperature spikes or rain falling on snow, alongside human activities like snowmobiling and disaster strikes. The impacts completely devastate mountain economies, block crucial supply chains, isolate entire communities, and heavily impact seasonal tourism. And finally, bringing it all together in Part 5, disaster risk reduction.
So how do we fight back? Well, the universal framework adopted by agencies like the United Nations Office for Disaster Risk Reduction follows a really strict cycle. It always starts with continuous hazard monitoring and detection. That raw data feeds right into Step 2, analysis and warning generation. Now, Step 3 is often the critical bottleneck, public alert dissemination. Simply put, a warning is completely useless if the public doesn't actually receive it. And finally, Step 4 is evacuation and emergency response.
So the crucial point here is that while the risk reduction framework is universal, the actual tools we use are highly specialized. For volcanoes, geophysicists use satellite INSAR, tilt meters to actually measure the ground swelling, and gas sensors. Tsunamis require a massive network of seafloor seismometers and deep ocean pressure buoys. And for avalanches, we rely on digging physical snow pits and using ground-penetrating radar. Remember, mitigation is just as critical as, but distinct from monitoring, ranging from strict coastal zoning against waves all the way to using controlled explosives to safely trigger avalanches before they have the chance to grow too massive.
But as examiners and scientists, we have to remain analytically objective about the limits of our science. As our source material points out, predicting the exact behavior and impact of a tsunami is deeply complex due to varying ocean depths, coastal topographies, and a whole host of other factors. Sometimes our warning times can only be measured in minutes. False alarms breed public complacency, while late alarms result in unimaginable tragedy. It is, without a doubt, an incredibly difficult governance challenge. I'm going to leave you with one final analytical thought to chew on. As climate variables shift and evolve, remember this. We cannot govern the tectonic plates, but we absolutely must govern our proximity to them. Are our current early warning frameworks truly resilient enough? Or are we just building better sensors for disasters we still can't escape? Think about that as you continue your prep. Thank you so much for joining me in this explainer. Stay curious and keep learning.